Welcome to Spaceverse, your portal to cosmic adventures. At some point, Naaman Bajaj had looked enough into the literature to know that what he was seeing was real. Sitting alone in his office at the University of Arizona, surrounded by computer monitors and the quiet hum of his workspace, Bajaj stared at the precious data that had helped complete his trilogy of published papers that all tackled one big, unanswered question in modern astronomy. Why do some planet-forming disks creep onto their own stars? It's a loaded question. These disks are where planets are born, spinning around young stars like celestial cradles of potential. They're made up of gas and dust, and under the right conditions, they give rise to new worlds. So when scientists saw that some of that material wasn't becoming planets at all, but instead mysteriously falling into the very stars it orbited, it raised more than a few eyebrows. Bajaj had just wrapped up years of research. His 3 studies were done, robust, interesting, and complete. But before closing the door on these final data points, delivered by none other than the James Webb Space Telescope, he decided to ring them for all they were worth. Just in case. And that's when something unexpected happened. His advisor was away for a month, off at a conference. So Bajaj, like many curious minds left to their own devices, began to play with the data. What more can I do? He asked himself. Is there anything more this data can tell us? He certainly didn't expect to open yet another door. Let's rewind a bit. To understand the significance of Bajaj's discovery, we need to go back to those first 3 papers. All 3 focused on the dynamics of material-filled disks around young stars. These disks are crucial to astronomers because they're the birthplaces of planets. Yet some of this material doesn't stay in the disk or become a planet. Instead, it falls inward onto the very star it surrounds. That's the puzzle. For example, Bajaj explained, the Earth is going around the Sun, but it's not falling into the Sun because it's constantly going around in that orbit. And he's right, Newton's laws tell us that unless something disturbs an orbit, the object stays in motion. So if disk material is spiraling into stars, then maybe something is disturbing that orbit. It could be a loss of angular momentum. But to lose angular momentum, the disk might need to shed some of its mass. So, how does that happen? This became the central question driving Bajaj and his collaborators. In their first paper, the team showed that strong winds could be lifting material vertically off the disk. In the second, they calculated how much material escapes as high-speed jets, narrow, focused streams of matter blasting away from the system. Then came the third paper, which compared mass loss through winds and jets to tie everything together. The dataset for this third paper came from 4 young stars in the Taurus star-forming region, about 457 light-years from Earth. But one of those stars, TAU-04 2021, stood out. The jet it emitted looked too perfect. This one particular object stuck out because it was so symmetric, Bajaj said. It's probably the best case of jet symmetry that we have seen so far, I would think. And that symmetry? It was a clue. In this context, symmetry refers to the 2 lobes of a jet, one shooting above the star, the other below it. If those lobes are uneven or uncoordinated, it might mean their shape is being influenced by the surrounding medium, interstellar gas, dust clouds, or gravitational fields. But if they're symmetrical, that suggests something more profound is at play. If the 2 sides of the lobe have nothing to do with each other, then it's probably the surrounding medium, Bajaj explained. But when you find symmetry or even anti-symmetry, it tells you something more. And what does that something more point to? A binary star system. A single star with a disk can produce jets, but the kind of perfect, balanced symmetry that TAU-04 2021 exhibited hinted at a different origin. Perhaps the jet wasn't coming from the visible star's disk at all. Perhaps it was coming from another, unseen companion. That's when Bajaj had his light bulb moment. My first reaction was, "Oh, this is awesome," he said. This technically would be my own sort of first discovery in a sense, so I was very excited. But almost immediately, doubt crept in. But what do I know? He thought. Of course, science demands evidence. So he tested his hypothesis, running models of known binary star systems to see if the patterns matched. And they did. At some point, I had looked enough into the literature to know that this is real. He had found something the astronomy community had missed, something hiding in plain sight, thanks to the massive scale of the universe. Just one pixel in the image he was studying covered a space of 14 astronomical units. That's 14 times the distance between Earth and the Sun, roughly 1.3 billion miles or 2.1 billion kilometers. In that tiny pixel? 2 baby stars. Let's talk specs. The 2 stars are separated by about 1.350, that's only a little more than the Earth-Sun distance. In cosmic terms, that's really close. One of the stars is about 0.33 solar masses, and the other just 0.07, not even a tenth the mass of our Sun. They're both so young, they haven't even started nuclear fusion in their cores. They're still growing. And surrounding them is a massive disk of material. Bajaj estimates that the disk contains micron-sized dust grains stretching up to 250 EYYU. That's nearly 27,000 times the diameter of the Sun. And the full disk could extend up to 500 EYYU. For comparison, the Kuiper Belt, the icy region beyond Neptune, only reaches about 50 EYYU. Even in cases of binaries, for this particular mass of the star, I think it's still an outlier, Bajaj said of the huge disk. And this changes everything. TAU-04 2021 has been well studied, particularly with the James Webb Space Telescope. Scientists loved it because of one special feature. From Earth's point of view, we see its disk edge on, like a dinner plate held at eye level. That's rare and extremely useful. Because the disk blocks much of the star's intense light, scientists can study it in detail without being blinded by brightness. That means more accurate models, more refined data. But all of that data is based on the assumption that there was just one star at the center. There have been multiple studies with jwst, and yes, they will be impacted, Bajaj said. That's because disk models often include a key parameter, where the disk begins. Before this discovery, some models placed the inner edge of the disk at 1.2 EYYU. But now, with 2 stars in the middle, Bajaj estimates that it should be more like 4 EYYU. That's a huge difference. A lot of them are about modeling what is happening at the disk, Bajaj explained. And that will lead to so many different things. Despite the chaos it might cause in the modeling community, Bajaj is excited. Because this is what science is about. These are the questions that missions like the James Webb Space Telescope were built to raise and to answer. These James Webb Space Telescope data sets are so beautiful, he said. And he's not done yet. Bajaj is now going back to look at the other 3 stars from his study. He has a sneaky hunch that another one might be a hidden binary too. He's also investigating whether TAU-04 2021 might actually host 2 jets, one from each star. And he's hoping that NASA's new Sphere X Space Telescope might help confirm those details. So there you have it. A discovery born not from a grand campaign, but from quiet curiosity. A month alone. An astronomer asking, is there more? And the universe, as always, whispering back, yes, there's always more. And that's it. If you enjoyed this video, don't forget to like, subscribe, and drop your thoughts in the comments. What do you think about the hidden binaries and mysterious disks like TAU-04 2021? Could even more of these systems be hiding in plain sight? Stay curious and keep looking up.